All right, what are we doing now? There's a primitive root mod p to the e. We proved it last time on Tuesday, mod p, right? Now we're pushing to the p second, p to the third, p to the fourth, and what are they claiming? Still has primitive roots. This is very number theoretic here. C mod p looks like more of an abstract algebra kind of calculation. This is actually number theory calculation we're entering. All right. So if you're asked to go to the next level, p squared, for example, you know, you have more experience than freshmen. So this is your thought. All right. I have a primitive mod p, right? And then you just hope that that's still primitive mod p squared, right? Still hope the primitive mod p to the third still is a primitive mod p to the same number happen to be the primitive root remains forever as you enter in higher. Wouldn't that be great? Yeah, and it is. It is true. Little caveat, but it is almost true. That's our hope. So seniors are more careful. They don't claim it. They just maybe. All right. Okay. So why is number one true here? Why is this statement true? Anybody? G is a primitive of mod p, right? If you raise to that power, you get automatically one. Why is that true? Phi of p to the e. What is phi of p to the e? Right? P to the e is a p to the minus 1, p minus 1. So that's exactly number of elements in the root unit. Everything is going to be 1. Doesn't matter, g is a primitive root, right? Yeah. All right. If this happens, that would be great. If you lower the 1 power, it's not 1. It's a good indication that it is going to be a primitive root, right? But we still have to take care of the other part, p minus 1. Isn't that right? The other part, if you look at other maximal divisors that's not coming from p, lowering p, that should be not equal to 1, right? If that happens, then it remains as a um, primitive root mod p to the e. So that's what we have to establish. Good? So it turns out this is sufficient condition to conclude it's a primitive root. And that I turned it into an exercise. A little bit challenging exercise. If g to the, this is actually no condition, I think you have to strike that out because we just showed that this is all satisfied all the time, right? So it's really the second condition. You don't have to worry about p minus 1. If you lower this power 1 by 1, and if you have that fact, it's not 1 mod p to the e, automatically its order is the full order, is the primitive root, right? But this time it uses g being a primitive mod root p. So I want you to take this condition or about the other condition and reduce mod, go down to the mod p, not p to the e. So this is a bit challenging, but let me guide you a little bit at the beginning part. This is our number 3, right? All right. Okay, that takes care of a one maximal divisor. Would you agree? One maximal divisor taken care of. So what you have to take care of is that let Q be a prime divisor of what? We took care of a p to the e part, right? There's a lot of prime probably involved in here, right? So it should be prime divisor of p minus 1. How about that? Is that right? Okay. So what was the condition? To guarantee that this is going to be a primitive root, the useful lemma, right? We should check g raised to the what power? P minus 1 divided by q, and there should be the full p to the e minus 1. Without q, that's a full order, right? Phi of n. Now I divide this one by q, so that will be the maximal divisor, proper maximal divisor. Then we have to show this is not congruent to mod what? P to the e, right? Okay. So in that level, p to the e, this is all the maximal divisors is coming from p minus 1. They're not equal to 1, and we just assume that this is not congruent to 1 mod. Then it proved G has this order, primitive root mod P to the E. So you're asked to show that, right? So what are you going to use? Answer is not Chinese remainder theorem, not Bourdieu's identity. What are you going to use? Not log, the property. What's the hypothesis of what we're going to use? No. I stated here, but did not implement the hypothesis of this lemma. What is it? Hypothesis of lemma. Is this one is kind of in the realm of this one. This one is not used, right? You have to use that. The fact that G is actually primitive root mod what? P. If you use that, maybe you can show that. So how does it start? Suppose, right? Suppose what? This is congruent to 1 mod P to the E, right? Suppose that. And struggle to find a contradiction. Suppose it is congruent to 1. That's all about mathematics, struggling, and smile at the end. Suppose it is 1 mod. What goes wrong? What was the hint? Go to mod P. Don't stay at the P to the E. Yeah. Go to mod P. If something is equal to, congruent to something mod P to the E, do you think it is still congruent mod P? Think about something is A is congruent to B mod, 100. Do you think it's still congruent to each other mod 10 if you reduce it? What do you think? Something is divisible by 100 is still divisible by 10, right? A minus B is divisible by 100. Is A minus B divisible by 10? Yes, right? So this one will allow you to go to mod P. Now, do you see contradiction? If not, just state that this is congruent to mod P and stare at it again. State it and use everything you know about mod P. This is the senior's dream, right? But that's the name I made up. It's not really the freshman's dream. It's just P power. You can do something about this P power. P power actually, yeah. Do you see that? Yeah. So I'm going to state that since I asked you to do that. So is that P to the E minus 1 equals congruent to 1 mod what? P. So what's wrong with that? What's your thought? How about this? What are you going to do about that guy? Something raised to Pth power? About that. What theorem comes to your mind? How about if I erase this? What theorem comes to your mind? Fermat's-Little theorem, right? So what is it? Congruent to A, right? A to the P A, A to the P minus 1, 1, right? Okay, so if you do that, of course it remains the same, right? So you see that P is irrelevant now? You can get rid of it. Is that correct? So by what? Fermat's-Little theorem, we have G raised to P minus 1 over Q is congruent to 1 mod P. Isn't that right? So what's wrong with this? Yes. It's okay. Yeah. Euler's theorem. Primitive roots. But this guy have a lower power congruent to 1. Therefore, G is not a primitive root, right? Mod P. That's the conclusion we are forced to derive from this situation. Therefore, it's not 1, right? Any maximal divisor that's coming from this reducing P minus 1 will never reach 1. It's going to be always not equal to 1. Fair enough? So this is given from a primitive root. All you have to check is this guy, raising it to p power. Make sure that is not congruent to 1 mod p, and then you're guaranteed that the guy you're looking at here is a primitive root higher level. This is thing to check now. Like I said, this is automatic from Euler's theorem. This is the only thing to check according to the lemma. All right? Okay. All right. Then let me start like this. Primitive root and p to the, g to the p minus 1, doesn't matter if it's primitive root or not. This is going to be 1 mod what? P if it's primitive root. Let's write it as an expression here. G to the p minus 1 is 1 plus, not congruent. How would you write this one is actually equality in integer level? What would you write in here? P times, right? Quotient. So they write k first in here. That's the statement. G to the p minus 1 is primitive root or not, it looks like that. Is that right? Yeah. So they wanted to go to next level. We want to consider that as a p squared, right? And see if that remains as a primitive root. That's all. That's their goal. What do you say? Let's compare that with the lemma, and we have it up there. To see if the g remains the primitive root mod p squared, all you have to check is this guy here, right? What is e here? 2. What is this one saying here? P to the e minus, so e is 2. So that is the guy to check, right? Make sure this is not congruent to 1 mod p squared, right? It must look like that. So if this is not 1 mod p squared, that's the statement we want to establish, then g is a primitive root, right? Is equivalent to condition on k. What would you say? There's already one there. When is this 1 mod p squared? When k is divisible by p. Is that right? So that is divisible by p. Not divisible by p, sorry. Not divisible by p, then it is not congruent to 1 mod p squared. Divisible by p, it is congruent to 1 mod p squared. So this condition we want depends on what kind of k we have after we raise to p minus 1 power. Is that okay? So if you actually raise that p minus 1 power, express it as 1 plus k times p is not congruent to 1, not congruent to 0 mod p, then g is a primitive root mod p squared. And nice thing is that from that point on, it remains forever as a primitive root squared, nothing to check. Okay, so I'm going to state that here. G is a primitive root mod p, and g to the p minus 1 is going to be stated like that because of Fermat's little theorem. It has to be 1 mod p. But if that k happens to be not congruent to 0 mod p, then because of the lemma, this g remains as the primitive root mod p squared because of the earlier lemma. Hope that makes sense? There is this p to the e minus 2, right? Is there, that checking in there. Good? So that's the good news. Probably the probability that you're going to land on a 0 mod p is far, less than the other case. So most of the time you're going to hit it. The next thing is what if we hit that k is actually 0 mod p, right? Next thing is also interesting. In that case, you don't have to go grabbing another primitive root. They have interesting solution, very number theoretic. All right, g is a primitive root mod p, right? And I raise a p minus 1 and 1 plus kp. K happens to be 0 mod p. That's the worst scenario, right? With a low probability of happening. What are they saying? Choose. I forgot to write. This should be the first. G1 is a G plus P. Let me write that down here. Just state it there. If G doesn't work because of that, why that G doesn't work, right? If G doesn't work, we can choose G plus P. G here versus G plus P. How does it change in mod P? It doesn't change anything, right? The congruence class mod P, these two things are the same by adding P. But it makes a difference in mod P squared level, right? So rather than choosing G, just add P in there, and it's the same congruence class, but different representative. And they're saying that number will guarantee that if you raise that to P minus 1, that's still primitive root mod P, right? I didn't change the class. And you guarantee that this time the coefficient K1 is not congruent to 0 mod P, just by adding the P in there. Now, we have started with a G. That was a bad one because of that. You switch to that. Now you don't have to do it ever again. It remains forever a primitive root to all the higher level, including P squared. So that's the end of the story. The answer, or whether we can prove it or not. That's how you find the primitive roots. So if you're asked to find the primitive roots mod 121 star, find the primitive roots. What are you going to do? You go down to 11, right? That's not too bad, right? Not too bad. And actually checking this one is also not too bad because P is relatively small. So find a primitive root G, or consider G plus P. This is a criteria now. Whether as you expand that to mod P, and it's going to be 1 mod P squared or not, then this will remain a primitive root up there. If it is a third power of 11, and so on, it remains forever. Does that make sense? Okay. All right. Do you think we proved that one, Lemma? What do you think? What do we need to prove it? Let me show you. If I write this one down, maybe you can relate it. The G to the P minus 1, P to the E minus 2. Right? That was a lemma. If this is not congruent to 1 mod P, we understood it's a maximal divisor, maximal proper divisor. It's not congruent to 1 mod P. G is a primitive root. Remember that? So that's exactly that. P minus 1. E here is a 2, so it's a P to the 0. So that condition not being 1 mod P squared is this condition. So it is like a corollary to that one. But how about this one? If G to the P minus 1, 1 plus KP, and if the case is 0 mod P, and we consider G plus P, and raised to P minus 1, wanted to show it can be organized like this, right? So if you have A plus X raised to nth power, it's a binomial theorem, A to the n, right? And choose 1, A to the n minus 1, one lower power, X shows up, and everything else has that shape. The tendency of the modular arithmetic, this in our calculation, this is going to have high enough power, so it's going to be all congruent to 0 mod something, right? And only this matters in here. Fair enough? So let's try that. Let's try to prove this one, lemma. And what you have to do is that raise G plus P to what power? No, not squared. What you have to test is this, right? To new G1, if you raise the P minus 1 power, you have to expand it, be able to show that it's 1 plus K1 times P, where K1 is not 0 mod P, right? So what are you going to raise this G plus P? To what power? P minus 1 power. Right? So proof starts like this. G plus P, right? Raised to what power? P minus 1. Then use this formulation to show this can be rearranged into that form such that K1 is not 0 mod P. Right? Oh yeah. Right. I apologize. Totally. This should be p minus one. That's what you're saying. Apologize. That whole power is p minus one. Whole power is p minus. Thank you. Being patient. Yeah. Yeah. That's it. That's about it. Yes. But I was focused on this one. J is at least two, right? So that one is here, right? Okay. So nonsense here. All right. That is 0 mod p. That is 0 mod p. Right? That's k0. Who can explain why the k0 I bracket in there that is not 0 mod p, right? Then I conclude that thing is not 0 mod p. Is that right? So here I'm looking at that guy. That's not 0 mod p. Why is that? K0, which is by definition is this, g to the p minus 2. It's mod p, right? Well, that's p minus 1, isn't it? And g, p minus 2. It's relatively prime to p, right? This is relative prime to p. So that's not. What's that? Yeah, I just bracket up to here. The p appeared in this part. So it's clear that k plus k0 to pr is not congruent to 0 mod p, correct? I want you to look back and just kind of be able to summarize it. So what? What does that mean? I want you to look at that lemma, be able to kind of wrap up. All right, we're here. What does that mean? G plus P raised to pth power is organized in here like this. 1 plus, I'm going to write K1 now. K1, P in there. That's not 0 mod P, right? So this G plus P had that property. If you have that property, P minus 1th power is written like this with not congruent to 0 mod P. And that G1 remain forever primitive roots. So at the very beginning, fine tune it with the plus P, and you have this precious primitive root forever for all the higher power. Make sense? G or G plus P. That was the summary. All right. Then, okay, so we have primitive, we have to show that what happened if you raise that and higher power. This was easy, that if it has that property, we can choose that G plus P so that we have this property and it is primitive root mod P squared. If you keep raising the power using the binomial theorem, they realize that they keep this form in here. So I'm going to state that this stage, not going through this calculation on your own, not easy to motivate with the statement, but you can imagine, all right, we start from here, raise to the next power, another p power to throw in more power, and modulo out, tails just becoming 0 mod something, p to the something. Maybe you could witness that, oh, it's always in that shape where this coefficient is in that. As you raise the pth power again, pth power again, pth power again. So how are you going to prove something like this? It's all about E changing, right? So we're going to use induction. If this is true, raised to another pth power using binomial theorem, then you show this continue the shape, right? So we're going to do that later. But I want you to look at this lemma and be able to conclude important statement in here. An important statement. That's our next exercise number, what is it? 4 or 5? 5, right. Um, write a nice corollary. of this lemma. Think about that senior's dream, that statement, right? If you establish that if this is so, then you establish something is something. All right. So does already know the answer? How about that g to the p minus 1, p to the e minus 1? How about that one? You know that one, right? Is congruent to what mod what? It has nothing to do with g being primitive root. Always work. 1 mod p to the e. That does not require primitive root, right? But how do you know? What other thing do we have to do to ensure g is actually primitive root? One maximal divisor, right? What is that one maximal divisor? So divisors of this, right? You don't have to check all the divisors, only one maximal divisor. What was that? One that is lower than that. If this is not, then conclusion, G is a primitive root mod p to the e. That was the statement. Important. One check, then you're good in p to the e, right? So what has it got to do with this lemma? Look at the lemma. We had that exact power in there, right? Is this 1 mod p to the e? Or is it 1, right? But is this divisible by p to the e? It has p to the e minus 1, but this guy is not divisible by p, right? Therefore, it is not going to be divisible by p to the e. Therefore, this is not congruent to p to the e. Is that right? So that establishes this fact. Therefore, g is a primitive root. All right, so if we can prove this one, it remains like that all the time where p is greater than or equal to 2. Then we're guaranteeing that the g or g plus p we fine-tuned at the very beginning remains forever as a primitive root. That was the statement. Again, how are you going to prove that star? Method induction. Thank you. I already saved this? No. No, I'm sorry. Hit the wrong button. All right, you seem excited about this induction we're about to do. So let's do it. All right, let me erase that. Okay, how about E equals 2? What's that? No, it is Euler's system, so it is 1 mod p squared, right? But it says nothing about there's this, k times p in there, right? I think this one is the E equals 2k's, is it not? The hypothesis itself is the case where E equals 2, isn't that right? So we assume the E equals 1 is true. So do the remaining part. Okay, if this is true E, is that true for E plus 1? Okay, so state that one, also E plus 1 statement, and you know which one to prove. So I think that's the hint. The same binomial theorem, organized conveniently for you. We're about to do this one, something raised to pth power, right? P minus 1 is already there. To raise to the next level, all you have to do is raise everything to the pth power. So we are looking at right-hand side, looks like this 1 plus something. So you're raising that to the pth power. It looks like this 1 and p choose 1. These are correct. No. And look at the powers of here. with the beginning power, we realize that, oh, that's high enough, probably 0 mod something. Okay, so assume, what are we assuming? G to the P to the E minus 2, P minus 1 power is equal to K, 1 plus K. I'm just going to call it 0 to ease this index. P to the E minus 1, K0 is not 0 mod P. And E is greater than or equal to 2, right? We start from there. And G to the P, if you raise the next level, then it's a E minus 1, is that right? That we enter that by raising this one to pth power, correct? You raise both sides pth power, then you change the level to the next level. You have to expand this one out and organize, this is our goal, to 1 plus K1, P to the what level? Not E minus 1, that's less. So next level, P to the E, right? That's what we want. And K1 here, it's still not 0 mod P. This is our goal. You expand this thing in here, organize it nicely to pull this shape out. 1 plus K1 times P to the E, and show this K1 is not 0 mod P. This is how I remember about binomial coefficient. P choose j is a p factorial divided by p minus j factorial divided by j factorial. Magically, this is an integer, but nothing touches the p, right? P's up there is not big enough, it's smaller than p, and there's no factor of p coming in there. P minus j also, right? Because j is greater than equal to 2 here. So there's no appearance of p if you factor it. So p survives. Therefore, in there, there's extra copy of p in there. And here, this one, I argue that it's greater than equal to 2, e. So together, we have at least e plus 1 copies of p in it. This one, I have p and p there, so p to the e in there. So for sure, they are organized in this way. So if you factor out p to the e, because of k is 0, non-congruent to generalized p, we pull it out. Make sense? All right. So I want you to look back on this lemma and see if you remember the conclusion. Remember the corollary of this lemma? Anyone remember the corollary of this lemma? What was that? Then it's primitive roots. Yeah, yeah. And this one says G is a primitive root because of this condition there. Yeah. Excellent. Let me go back to here, the theorem. There is a primitive root mod p to the e for all primes p, e greater than or equal to 1. Right? So we have proved that. Take the primitive root in mod p. Think about g or g plus p. Once you choose the right one, it remains forever the primitive root. Great news. You don't have to do any calculation. Fun proof. A lot of binomial coefficients without that. All right. Well, next thing I was showing was the z mod a star. It does not have primitive root. It was the very first example we tried. It does not have primitive roots. And next thing you can say, if not, 1, why not 2? You see that? Play with the 2. And it is true. Z mod 8 star generated with the 2 elements. Compared to the size of Z mod 8, which is 4 elements, is too much of use, right? But it miraculously survives like that. Z mod 2 to the E star is never a primitive root. But there's always a 2 generator. This 2 generator never even change when E is changing in there. -1 and 5 will generate everything. That's their story. All right? This e to the 2 to the e power has a special structure, not primitive, but very, very close to primitive. 5 to the b, that has almost the right order, just missing factor of 2 coming from -1. So it's almost cyclic. Cyclic cross Z mod 2. That's the structure. So that ends the entire analysis, all boiled down to, let's see if I can go back, all boiled down to that. The structure of all that, even in this all odd prime, we just saw that they're all primitive, and you know how to calculate orders, how many orders, elements of orders are there. It's all coming from this Chinese remains theorem. That concludes that entire chapter. All right. Okay.